Okay, so let's take a look at this fact now. If we have two series, both of which converge, then if you multiply a series, every term of the series by some real number, uh, then that's also going to converge. That's also going to converge. In fact, it will actually converge if the first series converges to, say, the letter A, then this would actually converge to C times A. And likewise, if the two pieces both converge, then when you add or subtract those series, that will also converge. That will also converge. Okay, so the sum of two series converges. And so we're going to use these results in our upcoming examples where we're going to check for convergence. So now we don't necessarily know what something converges to, right? We won't necessarily know what something converges to, but we will be able to check to see if it converges. Okay, and so what we have series-wise right now that we can check convergence of, we can check convergence with geometric series. Right? We have geometric series, which we can check convergence of. And we have telescoping series. And now we have series that we can check with the integral test. Okay, so if our series, when we break it up, is any of those, then we look at the pieces and each piece individually. And again, if the two pieces converge, the whole thing will converge. Okay, so let's look at our first example here. Let's look at the sum as k goes from 0 to infinity of 2 to the k plus 3 to the k, all that divided by 4 to the k. Okay? So this on its own doesn't fit any of our things. Boy, this would not be fun to try and integrate, at least on its current form. So what I'm going to do is take the fraction, I'm going to break it up, and think of this as two different series. So sum as k goes from 0 to infinity of 2 to the k over 4 to the k plus 3 to the k over 4 to the k. And then I'm going to simplify both of those and write them as two different series. Sum as k goes from 0 to infinity. And what I can do here with the 2 to the k over 4 to the k is take the exponent, pull it out for a second, and I have 2 over 4. So this is just going to be 1/2 to the k. Plus the sum series as k goes from 0 to infinity of likewise 3/4 to the k. And then we look at what we have here. And we say, well, I have a ratio to the k. That's a geometric series. And the ratio is less than 1. So that series is going to converge. So, and likewise, this series here, 3/4 to the k, is also going to converge because it's a geometric series where the ratio is again less than 1. So we know that both of those are actually going to converge. So for both of those, we know that they're geometric series. So we know that they're going to converge, and so the whole thing is going to converge because of geometric series. That's it for the convergence problem. But in this particular problem, we can actually go just a little bit further. Because these being geometric series, we can talk about what they converge to. So my first series there, a is 1, and the ratio is 1/2. So that series would converge to a over 1 minus r, which would be 1 over 1/2, which would just be 2. And in my other series, a is also 1, and r is 3/4. So that would converge to 1 over 1 minus 3/4, which would converge to 4. So the overall series, even though it wasn't on its own a geometric series, rather the parts of geometric series, would actually converge to 6. Okay? And so here we have an example where we're able to use this result that the two pieces converge, and so we can talk about the convergence of the overall thing. And in this case, because it's a geometric series, not only can we talk about it converging, we can actually talk about what it converges to.